In Rutherford's experiment, alpha particles are being incident on the metal foil that is made up of gold, and scattering of those alpha particles will help us to find out how much is the size of the nucleus. And one more important character, that is distance of closest approach, will help us to find out the nuclear size. So first of all, we will define the distance of closest approach. Here, this one beam is being taken. It is of alpha particle that is being incident. This is an atom of the gold, and we have taken at the center its nucleus where the positive charge is also concentrated. Let this alpha particle is of mass m, and it is moving with velocity v, and this beam is particularly directed towards the center of the nucleus. As it approaches towards the positively charged nucleus, it is going to experience the repulsive Coulombic repulsion. Here it will experience the Coulombic repulsion and kinetic energy, because it is having velocity v and possessing kinetic energy. So that will convert into the electric energy here. At some distance, say r naught from the center of the nucleus, there is a moment when this alpha particle will stop for a moment, and at that particular point the kinetic energy of alpha particle will totally change into the electrical energy. And here the scattering is through 180-degree, and alpha particle is going to retrace its path. This particular distance at which this thing will happen, the alpha particle will stop for a moment, and whole of its kinetic energy will convert into the electric energy. At that particular point, we are having this distance as the distance of closest in approach, where entire kinetic energy of alpha particle gets converted into the electrostatic potential energy. So, by finding out this R naught, how we are going to estimate the size of the nucleus is the second point now that we are going to find out. Now, the charge on the alpha particle is equal to plus 2e, where e is the charge on the electron. Because alpha particle positively charged, it is having plus 2e. Charge on nucleus is plus Ze, where Z is the atomic number of metal foil. Here we have taken the gold because it is Rutherford's experiment. He has taken the gold foil. So here the atomic number is of gold. Now, kinetic energy of alpha particles is equal to half m v square. We have considered m as the mass of the alpha particles and v as the velocity. Also, electrostatic potential energy of alpha particles at r naught, that is distance of closest approach, is constant. The first Q is 2e and the another is the product of the two charges and reciprocal, the distance between two of them. Mark it as equation number 1 and this as equation number 2. Now we know the condition of the closest approach, where the kinetic energy of alpha particle will be equal to the electrostatic potential energy of the alpha particles. So taking the condition of closest approach and according to conservation of energy, kinetic energy of alpha particles is equal to electrostatic potential energy of alpha particles. That is half mv square is equal to product of and R naught. Now equating these two and rearranging, we will get the distance of closest approach is equal to this relation. K is Coulomb's constant into 2ze square upon half mv square, that is the kinetic energy. Coulomb constant, we know that value is 9 into 10 power 9. Z is 79. It is the atomic number of gold. Charge on electron is 1.6 into 10 power minus 19. And the kinetic energy provided to the gold atom is equal to 1.48 into 10 power minus 12 joule. On putting all these values in this relation, we get the R naught is equal to 2.5 into 10 power minus 14 meter. Now, there is one more approach to find out the closest approach. Here, the kinetic energy of alpha particle, if it is very large, in that case, the alpha particle will reach very close to the nucleus. And in this condition, the nucleus will not remain a point charge, and hence the Coulomb's law won't be applicable. And moreover, the nuclear forces will also come in action. So alpha particle, instead of returning, it will penetrate the nucleus. So we found out that there is a certain limit where the kinetic energy will penetrate the nucleus, and the alpha particle won't return back. So this condition is going to decide the radius of the nucleus. And on the basis of this, the gold nucleus is estimated to have the value 6.9 into 10 power minus 15 meter. So from this we conclude the radius of nucleus is of the order of Fermi.